When you fly a standard consumer drone, the flight feels incredibly smooth. Under the hood, it mostly relies on classic PID regulation or more advanced cascade PID and gain scheduling. It's not very smart, it simply works. It's quick, deterministic, somehow reliable, and also certifiable. That's why it's used in commercial aviation and certified by FAA. But in a modern day, aviation progresses. We have things like eVTOL, which is short for Electronic Vertical Takeoff and Landing, and it does what it says. It takes off and lands vertically, and the flight itself is horizontal, where lift is generated by the wings, not by the rotors. The transition phase between takeoff and horizontal flight is highly nonlinear. You know what's also highly nonlinear? The Agile drone industry. Especially when considering autonomous scenario. Agile drones face extreme drag and other physical phenomena like turbulent downwash and ground effect. After considering this, do you still wanna try PID? A simple PID controller only reacts to the past. It cannot see the future to compensate for these crazy aerodynamic shifts. Perhaps we should look into the future. Here comes Model Predictive Control or MPC. In its core, MPC treats flying as an ongoing optimization problem. Instead of just reacting to the present, the controller calculates the optimal path by looking a set number of steps ahead. This mechanism of a forward-looking window is called receding horizon. Before a physical drone executes a single movement, the software simulates a series of future states, predicting exactly where it will be at each upcoming fraction of a second. The accuracy of those future states depends entirely on a system dynamics model, represented by the optimal control equation x dot equals f of x u. This is the mathematical engine generating those predictions. To account for extreme turbulences and other stuff we talked about, researchers partition this equation. Standard predictable physics are handled by first principles math. The chaotic, unmodeled aerodynamical forces are then predicted by separate neural network deep learning model. This way we can predict drone's state quite accurately. Computing this hybrid model perfectly requires significant processing time. Luxury the Agile drone moving at 20 meters per second simply doesn't have. But here comes the article I have chosen. It explains how to make such a complicated model real-time capable. That means making the drone control frequency at least 100 Hz. If the model iteration is not ready when needed, you guessed it, a drone will likely crash or behave unpredictably. But why is it so slow? Let's look at MPC equations at first. Our main objective is to minimize the cost function. In plain English, it means find the best sequence of motor commands U that results in the lowest possible penalty L over the next n future time steps. Xk is the state of the drone at step k, and Uk is the motor thrust you apply. The second equation, xk at 0 equals x0, it is a constraint that says that step 0 of the prediction must be locked exactly on the drone's current real-world sensor readings. The third equation is constraint for physical reality. It tells the solver that the next state must be strictly calculated by the physics model f over the tiny time step delta t. Phi represents mathematical integrator, in our case the fourth order Runge-Kutta method. This is our hybrid physics model we already talked about. The last one represents the constraints of the drone's physical limits, like maximum RPM of the motor. Looks easy, just solve it and control the drone, right? Well, no. This is nonlinear programming or NLP problem, meaning it is very time consuming. The first thing article does is make NLP problem a sequential quadratic programming problem. So we are actually trying to find the next best step delta omega I. Meaning, don't try to find the perfect flight path all at once, just find the best adjustment to make right now. Penalty function has been replaced by a quadratic equation which is shaped like a perfect bowl. Qk and Rk represent the gradient of the bowl and Hk is Hessian. The next equation is the most important one. The complex nonlinear physics and neural network aerodynamics from the previous image have been replaced. There are now two simple matrices, AK and BK. These are the local Taylor approximations. The complex hardware limits, like motor RPM limits, have been also linearized into straight flat walls using the matrices Gx and Gu. The bottleneck is that the computer must calculate the partial derivatives of the system to get those simple AK and BK matrices. Here, the strongest bottleneck is created by the neural network, because the system uses a fourth-order Runge-Kutta integrator, E equals 4, over a prediction horizon n. The solver has to calculate the derivatives of the neural network n times E times 2 times for a single optimization step. How to make it faster? Well, we approximate by Taylor series. This way, we create locally valid approximation up to second order around the current iterate. To visualize these equations and approximations, we can say that we went from this complicated problem to this beautiful locally valid approximation. This will incredibly speed up our calculations. However, they are still not real-time capable. The solution that article proposes is called real-time iteration. That means we only solve one SQP iteration. It will likely result in suboptimal solution. However, it will take no time at all and our MPC can run at promised 100 plus Hz. Or can it? We solved the real-time problem, right? Right. Well, unfortunately, the real-time problem isn't fully solved. Remember our neural network? It's massive, because it needs at least few thousands or tens of thousands parameters to be able to model our unpredictable aerodynamic effects. We already did the Taylor approximation we talked about, but that is simply not enough. The neural network is still there and it is huge. Imagine microcontroller inside a drone, but the controller has to run neural network by itself inside the optimization. To format data into a quadratic problem, the solver calculates the Jacobian and Hessian matrices for the neural network. This is where math compounds. It cannot just calculate these once, it must compute them sequentially for every step across prediction horizon. This will result in fatal bottleneck. The control frequency will drop under 1 Hz as the CPU is overloaded. Here is the last piece of puzzle to our solution. We are going to separate our neural network from the optimization solver itself. Here is our network and here is the solver. We'll use hardware which is optimized for parallel computing and we will run specialized software for neural networks like PyTorch. Instead of sequential derivatives, our highly optimized hardware like GPU evaluates the network exactly once per control cycle as a single batch. It computes a locally valid second-order Taylor approximation. And the solver is then provided with this approximation. It's quick, reliable, never late. Our job is done here. We finally achieved real-time control capability. Okay, let's look at it once more as a whole process. Okay, here we have variables xi and ui, which are drone state and motor inputs respectively. They go into neural network preparation phase as well as QP preparation phase. We will start with neural network preparation phase. Here, after first Taylor approximation is computed, the base value and Jacobian are sent into QP preparation phase. The QP preparation phase takes basic physics, combines them with the information from neural network and uses this data to linearize the continuity conditions, creating A and B matrices. It also linearizes the cost function as well as safety limits G. Then we have the so-called bowl-shaped optimization problem and we send all those 6 matrices into a feedback response phase. The drone waits for a fresh sensor reading from reality to finalize its decision. Once it senses its actual state, it solves the pre-constructed QP and sends the final command to the motors. Then the output to the motors together with drone's current state serve as input for next iteration. The article compares itself with so-called naive implementation, which means putting neural network right inside the solver. Starting on the left with a tiny multilayer perceptron, just 354 parameters. Both methods easily maintain control frequencies well above 100 Hz. But as the network scales up to 17K parameters, the naive implementation collapses to an unusable 20 Hz. The architecture from the article, however, remains completely stable. They also did a convolutional neural network stress test, where they tried using ResNet 18 with 13 million parameters. Their implementation achieved 63 Hz compared to naive, which froze completely. Here, however, they are twisting the narrative for effect. I'll explain at the end of the video. They also compared the tracking error over circular or lemniscate. The errors are comparable, however the control frequency is much better with the proposed architecture. They also did a very cool training of the neural network to compensate for ground effect, as the network can have enough parameters and still be real-time capable. So they basically added one additional input, which was the height map of the room, and they flew multiple times over a table, and they tracked the vertical position error. The blue lines show results they achieved with this. Quite impressive, don't you think? Well, and now the promised part. So, did they actually put the whole ResNet 18 with 13 million parameters inside an embedded Agile drone? Well, not really. If you look at the table, they used RTX 3000, which is kind of a big guy. And if you imagine putting such a thing on an Agile drone, well, I don't think so. Okay, let me say, this was a great article. I think it is important to mention that the findings of this article aren't limited to just Agile drones. The implications can be applied to any Agile systems, including autonomous vehicles and robotic arms.